Bohan sir, you can start.
Yeah.
Zan.
So, good evening, all. Today we are going to discuss about the conformation of cyclohexanes. Right. So, in the previous classes, so we are discussed about the conformations of like cyclopropane, cyclobutane, cyclopentane, all these things. Yeah. So, for the continuation here, the next the conformations is the cyclohexane here. Okay, so here generally all these are cyclohexane, means cyclic compounds. So already we know that where the conformation of cyclic compounds is different from the acyclic compound, because the acyclic compound, it is very easy to study the conformation analysis, because the acyclic compound you can rotate the carbon-carbon single bond and you can generate variety of conformations here. Okay, but in the cyclic compounds, so that facility is not there, because you cannot rotate the carbon-carbon bond here, because if you rotate that bond, so the bond breakage will be takes place. That's why we won't follow that rotation here, and it is not possible generally. And the only possible is you can flip the molecule and you can convert that particular conformation into the variety of conformations here. Okay, means you can flip that molecule. Flipping means by holding the one bond and you can pull out and pull in that bonds, right? And you can generate variety of conformations here. Yeah, and generally here the planar structure, right? So the planar structure is less stable than the puckered structure here, because the planar structure is having the more angle strain, right? Because the angle deviation, okay, the angle deviation is more as per the BST theory. BST means Bayer strain theory, right? So here the BST means Bayer strain theory. So according to this Bayer strain theory, right? So it tells about the deviation, how much deviation is there than your particular, if sp3 carbon or sp2 carbon or all other things here. Okay, and generally here we took up the sp3 hybridized carbons only, because only you can rotate or you can flip the carbon-carbon single bond here, right? So that's why in the cyclic compounds, right, where you can take the cyclopentane or the cyclobutane or cyclohexane here, right? So here you see where the bond angle, right? This is your planar structure here. Okay, for the planar structure, the bond angle is 120, right? So here the bond angle is 120 degrees, right? So 120 degrees here. So generally here you see it is a sp3 hybridized carbon here. Okay, see sp3 hybridized carbon. And generally the sp3 hybridized carbon bond angle is 109, right? It is 109 degrees 28 minutes here. That is the actual, right? The actual bond angle. And but it is okay. This cyclohexane is having it is showing 120. So how much deviation is there? So there is a lot of deviation is there, lot of difference is there, right? Because here the 120 minus 109, 109, right? So 109 my degradation 28 minutes minus 120. So how much it is? Nearly it is 111, right? It is 11. So 11 degrees something. This much deviation is there. So it okay. So it calls for the angle strain here, right? It calls for the angle strain. So if any molecule is suffering from the angle strain, right, or the steric strain, or any, all these are angle strain and steric strain. All these are the destabilizing factors, right? So this is the destabilizing. Right? It is a destabilizing factor here. So due to this angle strain, that particular molecule is become the unstable molecule here, right? So its energy is, what is that, more here. Okay, it's what is that? So the potential energy, it will be more. Okay, that's why that particular molecule is it will be having the less stability. Okay, So that's why to avoid this problem, right? So we will convert that particular planar structure into the possible stable structures like chairs conformation and board conformation, hop chair conformation, hop board conformation, or the twist board conformation. So all these are the different conformations of the cyclohexane here, right? So by flipping that molecule, by what is that, pulling out and in of that particular bonds, you can generate the variety of conformers here. Okay, right. You see here, first we'll see the chair conformation of cyclohexane, right? So generally here the chair conformation, right? So chair conformation, it is stablest, right? It is the stablest conformation. This is the most stable conformation among all the cyclohexane conformations here, right? Because the cyclohexane will be exhibits variety of conformations here, like chair conformation, board conformation, okay, twist board and half chair conformation. So all these are the possible conformations here among all the conformations where this particular chair conformation is a stable conformation, because you can see in the chair conformation. So all the bonds, right? All the bonds will be orient in the opposite direction here. Okay, if they are orient in the opposite direction, so there is no steric repulsions here, and the angle strain also minimized here, right? So that's why it is the most stablest conformation, right? And in the cyclohexane, you know that there are two kinds of bonds are there, right? The axial bonds and equatorial bonds here, right? So you see here, right? So there are six, right? So here, which is orient parallel to that structure, right? So this is the parallel bonds here. All the parallel bonds are here, sir, right? All the parallel bonds. These are the axial bonds. Okay, they are parallelly oriented, and these are the equatorial bonds. Means the perpendicular, right? So these are perpendicular here, and these are the axial. These are the parallel here. Okay, parallel bonds here. So based on that, the orientation, based on that, what is that? The position or the orientation of that bonds, we classified these two types of bonds like axial and equatorial, right? And both bonds, axial and equatorial, right? So here, this is your right. This is the so this is planar conformation. So in the planar conformation, you can see right here means it all these the orientation is right here. This is above the plane. It is a below the plane here, right? Axial is a above the plane here. This is the below the plane. So that's why both will be right. So they both the bonds are not on the same plane. That's why they won't suffer. They won't face any steric repulsions, right? So yeah, and here this particular right, the chair conformation will be right. The chair conformation, it is converted into the Newman projection formula, right? The Newman projection. So the Newman projection, it is best way to represent the right the conformation here, and from this you can see the orientation of the bonds, how they are aligned, are they anti-aligned the bonds here, right? So you can see here like simply you convert, right? So you convert this chair conformation into Newman projection of the chair conformation. Okay, and what are the right? The bonds are on the one plane, and what are the bonds are in the different plane? You can see here, right? So in this, okay, yeah. So in the right. So in this conformation, you can see here the 1, 2, right? So here you see the Newman projection, right? There are the 6 Gaussian butane units here, like here 1, 2, 3, 4, right? So what are those here? So one, then you can find that 1, 2, 3, 4 here. Okay. So like These are 2, 3, and 4. Right? And 2, 3, 4, 5. And the 2, 3, 4. Okay. And where is that fifth one here? Here is 6 here. Okay. So this. Yes. Right? So here you see these bonds, right? So 1, 2 here. There is one generally here. Yeah, yeah. Yeah, the one this the one carbon is that is away the plane here. Okay, and this is 1, 2, and 3. Right, 1 is a 2. Right, so the what is that? So that particular the ring. Okay, so here this is the 1 here, right, and here is 2 and 3, 4. Right, so these are in the Gaussian interaction. Right, so Gaussian means adjacently. Okay, so these are in the adjacent positions here. And like 2, 3, 4, 5. So these are also adjacent here. So like that, you can see the Gaussian interactions. And when you calculate that particular, how many Gaussian interactions are there? Are 6 here, right? And each will be contributes, right? Each Gaussian interaction will be contributes the energy 3.3 here. So totaling it is 19.8 kilojoule per mole here. Okay, so means here you see for each gauge interaction, you have the 3.3 kilojoules of mole per mole energy, right? So this much energy is required, okay, to keep that particular conformation in that what is that this conformation. So this much energy is utilized here, right? But in this right, cyclohexane chain conformation, right? So you see this, these are, right, the bonds are not, okay, they are not suffering from any the Gaussian interaction generally. So it is more stable than when you convert this Newman projection, it is somewhat the destabilizing Gaussian interactions are there. Right, now coming to this board conformation. So when you right, so pull this right. So just you pull out this carbon here, right? Just you pull out this carbon here, and okay, and this also. So this is also pull in inside, right? Just you pull this carbon inside and pull out this carbon outside here. Then it will be converted to board conformation, right? The board conformation of your cyclohexane. And yeah, now you see how they are, right? Means how the particular hydrogens are oriented here, right? You see here, you see in this particular board conformation, right? So generally here, this board conformation, it is not stable that much of your chair conformation, because in this board conformation, right? So where this particular, right? So here these bonds, right? These two hydrogens, they will be nearer to each other, and both are on the same plane, right? Same plane here. And you see, these are called the F. F means a flagpole hydrogens. Right? These are the flagpole hydrogens, and you can see the interactions of these two. So due to this flagpole hydrogens interactions, so it is destabilizing. right? Destabilizing factor, right? And here the C1, C2, C3, C4. And when you convert this into, right, so Newman projection, okay. So here you see the, yeah, right here the C1 and C4. These two are eclipsed. Right? These two are eclipsed each other. Okay, these two are eclipsed. These two are eclipsed. These two eclipsed. Right. So generally, if any atoms or the groups are eclipsing each other, so it is the least stable. Generally, the eclipsed conformation is the least stable, isn't it? Here you see, but you see in this particular conformation. So here you see this, yeah, right. So that there is a 60-degree separation, right? So these are in the Gauche. These are in the Gauche relationship, right? So all these hydrogens are 60 degrees and it is Gauche. Here also Gauche, here also Gauche, Gauche. So everything is Gauche in the, right? So it is stable. It's stable. Then you are this conformation. Here there is no, right? So all these are the eclipse here, right? Okay. So there is 0 degree. Theta equal 0 degree eclipse. Okay, all are eclipse. So you see that what is that? The what is both are means atoms are eclipsing each other, overlapping. Okay, so it is destabilizing factor. That's why the board conformation is not stable than your chair conformation. Okay. And this particular board further it is going to convert into the twist board, right? So that twist board it is somewhat stable than your board conformation because in that twist board, right? So where this okay, so here these hydrogens, right? So away, these are away here. These two are away from the plane here, is it? So you can see yeah, is a this both axial bond here, right? So these are equatorial and axial. There is a isoclinal bond, right? Here I means isoclinal. Yeah, isoclinal. Isoclinal means on the plane, right?
So these are the on the plane here, isocline, and these axial and equatorial above and below the plane here, right? So here you see that these bonds are not eclipsing here, right? No two bonds are eclipsing here. You see these are not opposites, right? So all are in the opposite direction. So generally here, right? So this is the stability order is this one, right? So here the twist board is more stable than board, okay, right? And here is a chair. Chair is a more stable than twist board than board conformation, right? So like that. Yeah. Next, ring inversion. So generally in the ring inversion, what happens here, where the axial becomes equatorial, equatorial becomes axial. So in that way, right? So in the normal cyclohexane, so this it won't means affect any you won't observe any affection, right? But here when that any bulky groups are there, then upon ring inversion, so you will get right. So you will explain the stability by doing the ring inversion here. Okay, because the axial becomes equatorial, equatorial becomes axial in the ring inversion. Okay, and here you see the ring inversion with the changing of right the orientation of the bonds will be takes place, and both will be right the axial and equatorial hydrogens will appear set to different chemical shift values in the NMR spectrum, right? So you see, for example, okay, so here the axial, they will be appear set to 0.45 ppm here, right? So 0.45 chemical delta chemical shift value. Okay. So like that, the where both the bonds will you can differentiate axial and equatorial bonds here, axial and equatorial bonds, right? So and it will can be explained by the deuterium exchange, right? So by deuterium exchange, you can explain the ring inversion of this particular uh, what is that cyclohexane, right? Yeah, and then the chain conformation, right? Here the board conformation it can be generated the twist board by twisting that board by flipping that bonds here, and in when in right so where in the twist board where the bonds will be right where the flagpole hydrogens will be they will orient in the opposite direction, so it will be minimize some what is that steric repulsions like that. In the chair conformation also it can be converted into the variety of further conformations in the chair here, like here is the chair conformation, okay, and it is going to convert into by twisting of that bonds here you can go to convert into half chair conformation, right? So in the half chair conformation you can see where the right so here in this particular right here is a 1 2 3 4 5, okay, and this is the 6 here, okay. So in this twist board sorry half chair, right, so where this C1 C6 C5 C4, right? So here means here where C1 here, okay, and C6 like this one, okay, and C5 and C4. So this is coming on same plane here, okay. So you see this is it will be right. So this will be appearing on means it is on the same plane, and this will be right C3 and C2, okay. So it is above the plane, right? So this will be upon twisting of this one, right? Upon twisting of this chain conformation. So the C2 and C3, right? C2 and C3, it is coming appearing above the plane here, right? Above the plane, above the plane. So in this way, you can convert the half chain, right? So it how it is appears here. half chair here, right? It appears like the half chair conformation. And then for the twisting of the particular half chair conformation, it is giving your twist board here, right? So it, and then for the in this twist board, right, it is going to convert into again the half chair conformation too, right? So in all these cases, you can see the changing of, right, the changing of the position of these carbons here, right, position of these carbons here, and finally we are getting the chair conformation too, right? Means here the chair conformation 1, right, it is converting into chair conformation 2 via, okay, it is changing via, okay, via formation of these half chair twist board and half chair 2 here, right? So in between this conformation means this conversion, right, you have to, okay, make these other conformations also, okay. And the way energy is half chair, generally half chair energy is 42 to 42 to 43 kilojoule here, right? So generally the half chair, and here the chair conformation it is 91, right? The chair conformation potential energy is 19 kilojoule per mole here, and the half chair conformation it is 42. So more energy, less stable, and less energy, more stable here. Okay, like that, where the chair conformation more stable here. Right. So means what we are doing here, the chair conformation 1. Okay. So we are converting, right? We are converting the variety of groups, different groups from one orientation to another orientation. For example, here you see where the HA and here the HB. For the differentiation, we are giving HA and HB. So HA hydrogen, it is axial here, right? So it is axial. Okay. So for example, in place of HA, any other group is there, like methyl is there, for example, just to assume. Okay. So if it is, if there is a methyl, so if it is at the axial direction, so it will be less stable, right? It will be less stable. So you bring that, bulky group with a bulky methyl group into equatorial, right? So by to bring that bulky methyl group, axial bulky methyl group into equatorial, you have to come via this conversion here. And finally, you see here HB is in the equatorial, right? So HB is so it is in the conformation 2. It is equatorial. It becomes axial, right? And this is axial, and it becomes equatorial. So like that, you can you can change the position of the atoms, other groups here. Okay. Yeah. And this is another type of right, the conversion here. So in whatever the, okay, the conformation is that, but the aim is to bring the changes in the position of the atoms here, right? So for that we are making variety of right, the intermediate conformations here, intermediate conformations. Okay. So by flipping of the bonds, you can generate variety of half chair board, then the other board, half board here, twist board. So like, okay, now we'll see the conformations of mono-substituted cyclohexanes. So actually here the means the conformation of cyclohexane, like substituted cyclohexanes conformation is very important here, right? For the substitute, because unsubstituted for unsubstituted cyclohexanes, right? So means it is not that much importance here, I mean, to discuss, because all the hydrogens are equal only. So no, there is no what is that the specificity here. But when that particular cyclohexane is substituted, either mono substituted or the di substituted or tri substituted, tetra substituted. So the conformation of these substituted cyclohexanes are difficult here. Okay, substituted cyclohexanes are difficult. And how do you assign the stability? How do you confirm the stability of the variety of substituted cyclohexanes, and what are the factors affecting on that substituted cyclohexanes? We'll see in this particular subtopic here. Yeah, right. You see, in this particular example where it is given the right, the methyl cyclohexane. Okay, here the methyl cyclohexane, and the methyl cyclohexane, this methyl group is right. It is equatorial, right? It is equatorial here, and upon conversion, right? So at equilibrium, right? At dynamic equilibrium, this methyl group is converted into axial here, right? This is axial conformer. This is equatorial conformer, right? And among these two, which is the most stable generally? Either axial or the equatorial methyl, which conformer is the most stable. So now you see the right, this particular mono substituted or the methyl cyclohexane by converting into Newman projection, right? Because the Newman projection formula is best representation. It is a best representation to explain the Gaussian interactions, right? Basically, we'll take advantage of these particular Gaussian interactions to explain the Gaussian interactions. So it is the Newman projection is the best representation. This is the best presentation. Now you see in this particular equatorial conformer and the axial conformer, right? So generally the equatorial conformer is the most stable. Always it is most stable because in the equatorial conformer, right? So this methyl group is away, right? So away from this any hydrogens, like you see, there is a okay, is a hydrogens are there, here hydrogens are there. So it is away from that, right? And yet this black hole hydrogen, it is not. It is that this much spatially separated. The methyl and that particular hydrogens are spatially separated, and it will be explained by this. You see, right? Right. Okay. So here you see, if it is the methyl is in the axial orientation, right? Now you see here the methyl axial orientation. So like the three hydrogens, right? This is on plane here. This is out of plane. Sorry, this is above the plane here. This is below the plane, and this is on the plane here. These three orientation of the hydrogens here. Okay. Now you see this methyl group, right? So generally here these two hydrogens are not interacting with that other hydrogens here. But you see, right, the hydrogen which is right on the plane, the hydrogen which is on the plane, it is interacting with the C3 carbon and C5 carbon, right? So this is interacting with the C3 carbon, C5 carbon. So here you can see the C3 and right 1,3 diaxial interaction and 1,5 diaxial interactions here, right? So you can see the 1,3 diaxial. Here this is axial and here is the axial. Okay. So here you see the 1,3 diaxial interaction. So generally when it is interacted here, then it is destabilizing, right? Destabilizing. Okay. Okay. Now you see, and in this particular equatorial and axial of the Newman projection, it is best to method to explain, right? The best presentation to explain the this particular methyl substituted cyclohexane here. Okay, right. So when this particular equatorial conformer converts into Newton projection formula, right? So here you see, okay, right? Okay, here is the this is the methyl. This is CO2. Bridge, right? So this is the bridge carbon here. Right? This is the bridge carbon. This is your bridge carbon here. Okay. And here C2 and C5 are the bridge carbons. Now this is a methyl group here. The bulky group, methyl bulky group here. You see this much separation is there, right? There is here 120, 240. Sorry, 66, 120 separation is there, right? 66, 120 degrees separation is there. Okay. In the if it is in the equatorial, methyl is in the equatorial direction. So you see it is 120 degrees, right? 120 degrees separation. And coming to this axial, right? Here, this methyl bulky group here, and this is your CH2, right? CH2. So both are interacting. Okay. So here is a bulky group here, CH2, and here you can see the CH2 and the CH3. Okay. So repulsion, Gauche interaction. Both are in the Gauche relationship here, right? Because this is the bridge carbon here, right? You see, bridge carbon here. Okay, and this is a methyl. So both are interacting, both are adjacent. So both will be suffers from the steric repulsion. But here you see, like here is a hydrogen, only the small atom. Here is a hydrogen, small atom is there, right? This methyl group is not near to this one here. It is away from this. It is away from this CH2 group. Okay, so this much separation, 120 degree angle degree separation is there. Here is a 60 degree separation here, you see, right? So generally here more separation is there. So it is more stable, right? Yeah. So here the table is given like the substitutions, right? Upon the variety of substitutions, how they will impact, how they will affect on the stability, right? So presence of variety of substitutions, how they will be right effect on the stability, and what will be the their free energies, enthalpy values are the free energies here, potential energies. You can see presence of here the tertiary butyl group. Okay, the tertiary butyl group, presence of this tertiary butyl group. So its value is energy values. It is 20, and the substituent, if it is what is it? So the ester group, right? So where it is delta of G value is minus 5.3, and for presence of this one here, right? So like, okay, so ester, and here is a ester like 2 points. So like here the phenyl group is there. Okay, so its value will be 12 here, and amine is there. It is 5.03. So like, and this amine group is, if it is at axial, it is 5.03. If it is right, so in the equatorial, so like its value will be increases here. Okay, so like that, you can see the effect of variety of groups here, right? And if any polar groups are there, right? The polar groups are there, and how will be effects on that, right? Polar solvent and non-polar solvents. Their values will be depending on the polarity here. Okay, so like that, you can go through this table, and you have the values. Based on this, you can have an idea about that the effect of the bulky groups on the stability of substituted cyclohexane here. Okay. Now you see the tertiary butyl group. For example, here you see, right, the tertiary butyl group. When this tertiary butyl group is in the right, axial direction, right? So axial direction here, and so generally it is least stable. And when the tertiary butyl group is on the on this equatorial direction, then it will be more stable here because that can be explained by this. All right. So this like what is that? Yeah, numeric projection formula like your methyl cyclohexane, right? So tertiary butyl also it can be explained by because the tertiary butyl group is away from that. What is that? The interaction of the various C3 carbon and C5, all right? The C5 carbon bridge carbons here, C3 and C5 bridge carbons. So you see least means right, no interaction between the Gauche, no Gauche interaction. So generally it is uh, absence of Gauche interaction is the stability. It will be increases. Okay? Right. And here you see the isomers. Okay. So by this particular conformation analysis, you can differentiate the variety of isomers here, right? You see here, for example, the chlorocyclohexane. So chlorocyclohexanes that here by chlorocyclohexane, there are two conformers are possible, like when the chlorine is in the equatorial, so equatorial chlorocyclohexane, and when it is in the axial direction, so axial chlorocyclohexane here, right? And you see the when you record the proton NMR spectra, right? When you record the proton NMR spectra at different temperatures here, like at minus 100 degrees centigrade or minus 115 degrees Celsius. Okay, the both the spectra gives a different chemical shift values here, right? Because both are the isomers only. The compound, right? The compound structure, molecular formula is same, but the orientation of the group is different. Okay, the orientation of group, yeah, the orientation of chlorine is different here. So in one in the axial chlorine, right? When the chlorine is in the axial orientation, right? So the signal means the chemical shift values will be different, right? So generally, this particular, right? The axial appear set, the axial chlorocyclohexane, right? So the axial group appears set to delta 4.5 ppm here, right? So delta 4.5, and equatorial it appears set to 3.8. Means here you see it is 4.5. Means it is appears in the what is that downfield region here, right? And 3.8 it is in the upfield region. So like that you can differentiate the isomers here, right? The two isomers can be differentiated by this conformation analysis here, right? Yeah, now the conformation analysis of the disubstituted, right, cyclohexanes. So this is somewhat difficult than the mono substitution here because the two substitutions are right. The two substitutions are located on either on the same carbon or the different carbon. Okay, so now you see the how the substitutions are effect on the cyclohexane conformation. You see, there is a conformation of 1,1 substituted cyclohexane where the X and Y, just like these are the groups are in the cis and trans orientation here. First, we'll go with this particular, right, the alcohol. Okay, right, methyl alcohol, right? So methyl cyclohexanol, right? So here the axial alcohol and the equatorial alcohol. So like you see, among these two, the axial alcohol is obtained as a major product here, and equatorial is minor product. Okay, so because you see where in the axial alcohol, right? So in the axial alcohol, where this okay, so you see in the alcohol, right? In the methyl, when the methyl is in the equatorial conformation, equatorial orientation, yeah, where the three hydrogens, the carbon carrying the three hydrogens, these are okay away from the interacting hydrogens here, right? And in the equatorial alcohol, you see that these three methyl groups, right? Yeah, here you see these methyl groups, right? So we can expand this. Okay, so these are away from, right? So in the equatorial, you see here where these three hydrogens, right? Upon expansion, right? So these hydrogens are that. Right? Okay. And in the axial alcohol, you see these three hydrogens are away from here, right? So to this hydrogen, these are away. Okay. So they are away from this one. So you can see that most requires more stability to this one, right? And in the phenyl group, yeah, here also you see the this is yeah, right. So here the one methyl, one phenyl cyclohexane, right? Conformation. In this particular conformation, you see that this is the phenyl group, the axial orientation, and the methyl is in the equatorial, and here is a equatorial phenyl. So generally, in general, this is the most stable actually, right? Most stable actually this one. In general talk, which is the most stable here, but where okay, so due to some factors, right? So this will be the sorry, this will be the less stable. This is the most stable. In general talk, this is the most stable because the bulky methyl group is in the equatorial direction, right? But due to that some symmetry, right? Some symmetry factors here. So this particular okay, the axial phenyl group is more stable, and this can be explained on the basis of this one here, right? You see, when this particular right? Yeah, you see. So here you see this particular right? This when this equatorial phenyl group here, right? And this is axial methyl group. Okay, so right, so these okay, the phenyl group and the methyl group. So these are on the same plane, and it is these are interacting here, right? The interaction here. So these are interacting each other, right? So you see, okay, so the interaction, you can find this, right? You can see the interaction. Here also same thing. Okay. So because so you see these are the here the perpendicular, right? These are the in the perpendicular nature. So both are interacting, right? Interaction. So it will be suffers from the severe steric strain. It will suffers from the severe steric strain. And if it is in the equatorial axial position, if the phenyl group is in the axial orientation, right? Axial orientation. You see, this is above the plane here, right? Above the plane, and this is out of plane, right? These hydrogens are out of plane, and these right? These hydrogens are away from this phenyl group here. Okay, so there is no interaction, right? There is no interaction between these hydrogens and this phenyl group. Okay, because you see the orientation, right? Like you see, these are the parallel, somewhat the right, the parallel here, some parallel interactions here. So, like if you see the above one, right? Here you see where, okay, so here this methyl group, right? So this is above the plane here, right? This is out of plane, and here also same thing, right? So they are interacting each other, but here this problem is not there in case of this methyl, and because here you see, okay, here in methyl, right? So, right, right? So they are not near. This is far away, right? These are far away. So you can see the minimization of your right, the interactions or the steric strain here. That's why where the phenyl is in the axial direction, and the methyl is in the equatorial direction, that is the more stable, right? Next is non-geminal disubstituted cyclohexanes. Okay. Non-geminal means vicinal, right? We call it is a vicinal. Right? Vicinal die. Right? Geminal means on the same. Geminal, right? So geminal means same on same carbon here. There is a gem. Right? If it is on the different, this is vicinal. Right? Okay. So in this type of conformations here, right? So in this type of conformation, generally here you see, yeah. Right. So here you see this 1,2, right? 1,2 axial equatorial is a 6 here. Okay, 1,2 diaxial or di-equatorial is a trans, right? So axial equatorial is a cis conformer, and 1,2 di-equatorial or the diaxial is a trans conformer. Right? So generally here the diaxial, okay, or equatorial. Sorry. Right? So equatorial is more stable than axial equatorial, then axial. Right? The stability order is in the die substitution. Right? In the die substitution here, equatorial more stable, then axial equatorial, then axial. This is the stability order of the die substituted molecules or the compounds here. Right? So like this is the trans. This is also trans. This is your cis. Okay? Your cis. Okay. Right. So now you see here in this particular dimethyl, right? Yeah. So here in this confirmation, right? Here is methyl, and these two methyls are axial equatorial. Right? Here is a cis. Cis here. And isomers here. Generally isomers. These two are the enantiomers here. Right? Enantiomers. Then by flipping that particular molecule here, we can convert that conformation. Okay? So here the axial equatorial, upon flipping, we are converting this into equatorial axial conformer. Okay? And by 120, so again you get the it's what is that? So the enantiomer of that one. Right? Okay. Now you see in this particular, right? So in this particular confusion, right? See this there are extra downstream interaction. Right? Downstream interactions are there. But you see, when you convert this into the Newman projection formula, so like you see, assume it is a Sahas formula, right? So here, right, this methyl and this methyl on the same side. Okay, just we see, right? So in the Sahas formula, you can draw like this. CH3, the CH3, and there is a hydrogen, the hydrogen. Right? So the two methyls are in the same direction. Okay? And when you convert that, so, right? So when you convert this into, right? And this methyl will be, right? So it is, 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 right? So Right? So here the eclipse. Eclipse conformation. Okay. So generally for the eclipse conformation, generally it is least stable pattern, isn't it? For the eclipse conformation, least stable here. So the cis, right? Equatorial and axial is a cis one here, cis conformation. And you see these two methyls are eclipsing, right? Eclipsing here. That's why it is least stable. Okay. Now here coming to this axial equatorial, other equatorial. Okay. So in the axial equatorial, you see, right? Axial, here. Diaxial, right? Here you can see, just to assume, right? These are Sahas formula, right? CSC. So you say these are trans. Okay. Two methyls are in the trans direction, right? These are in the trans direction here. Or you can take di-equatorial here, diaxial here, right? Diaxial. And here is a, here also same thing. You see here. Okay. Just to assume in this chain conformation, here is a methyl, here is a methyl. Right? So this methyl, this methyl. These are oriented in the opposite direction. Okay. Now you see the potential energies of these. Okay. Where right. Yeah. Yeah. Right. You see here for this particular. Right? So this conformation here, this right, this CH2, right, this CH2 and this methyl, this is CH2 and CH3 bridge here, this is bridge carbon, and this one, they are the gauche, okay? And for this also, this two, okay, in the gauche interaction, right? They are gauche, it's gauche. Okay, so there are four gauche interactions are, and each gauche interaction, right, gauche butane interaction. So each gauche interaction contributes a 3.75 kilocalories energy. So because 15 kilocalories, right? And in the right, it's this equatorial, right? So di-equatorial. You see, there is no gauche interaction, right? The methyls are. So this is equatorial, okay, and here equatorial. There is no what is that gauche interaction, right? Because here you see, okay, so no interaction, but here you will see the, it will be interaction. Okay. Here there is no interaction. That's why you see here only one gauge interaction. That's why the potential energy 3 parts, so 3 parts. So this is a less stable, this is a more stable. And also something like 1,3 dimethyl cyclohexane. Right? So there are, when this diaxial, right? So diaxial, and what is that? 1,3. So in the 1,3 positions, right? So for this 1,3,
conformations means substitutions here, right? 1, 3. 1, 3. Axial and equatorial is trans. And 1, 3. Equatorial are axial is a cis here. Cis conformation. Right? So here the stability order will be, okay, the stability order will be axial, equatorial, most stable, then equatorial, then axial. So stability order. And you see the so here this is the axial equatorial conformation. This is a trans conformation. This is a stable conformation, right? So because the energy is 8.2, but for cis it is 15.5 here. So more the energy, so less stable. And this is okay. So more stability is the difference of this. Right? So like so many examples are there here. Right. Now the 1, 2 cyclohexadienol, right? So diol in the glycols are the diols, you can see this diol. Now in these particular conformations, the stability order of this one can be explained based on your the hydrogen bonding, right? Intramolecular hydrogen bonding. You can explain the stability because the intramolecular hydrogen bonding is a stability factor. Intramolecular hydrogen bonding is a stability factor here. Now you see where this in this particular trans conformation, right? The trans conformation where this particular axial equatorial, right? Axial equatorial where it is able to form the hydrogen bonding, right? Axial equatorial, it is able to form the hydrogen bonding because these two the groups are reasonable, right? Reasonably nearer here. So they will able to form the hydrogen bonding. And upon flipping of this molecule, you will get this particular axial equatorial. It is right nearer to this one. And in this equatorial conformation also, that kind of interactions means the hydrogen bonding can be observed. Okay, but in the diaxial groups, so that the interaction is absent because both the hydroxy groups are far away here. Right? That's why it is not possible to that formation of the hydrogen bonding. Right? So the stability order of this particular right dihydroxy cyclohexane. Right? So you can explain that where the particular axial equatorial and equatorial, right? Both will be equal. The stability order is axial equatorial that equal equatorial di-equatorial, then axial. Both are equally populated, right? Equally populated because hydrogen intramolecular hydrogen bonding, right? So generally this is more stable, but in the di-equatorial also that hydrogen bonding interaction is there. You can see, right? So here you see this, right? So that this is also more stable. Okay.
And when you see the means the right the existence of this one is, right? So this is the more stable than this one. It's less stable, right? It is not existence here because you see this is the even though it is trans, right? So where because of the orientation of the hydroxy group, so absence of hydrogen bonding here. And here you see the orientation is towards on means near on here, so you'll be able to form the hydrogen bonding. And the right the hydrogen bonding interaction may be more right strong in this cis conformation. Yeah. In the bromo compound also, you can explain the right that particular stability based on the right that bulky group interactions. Like if generally the trans conformers is the most stable here, and the cis is right so less stable because you see the due to the steric repulsion between these two conformers here. Right? And here you see the means 1,3 dihydroxy. In the previously it is 1,2 dihydroxy, but in 1,3 dihydroxy also you see actually di-equatorial and the diaxial. So generally here the diaxial is more stable, more populated here because the hydrogen bonding is possible here. Okay, so in the right in the 1,3, at the 1,3, right in 1,3, this is more stable here. And in the 1,2, diaxial is less stable. Okay, one because the orientation of the hydroxy group. In the 1,2, right in the 1,2 here where is okay, so in the 1,2 where the hydroxy group are like this, so these are far away, so no hydrogen bonding possible here. But here in the 1,3, right, this is 1,2 and 1,3, so where this diaxial here, where it able to form the hydrogen bond. And here in the 1,3 di-equatorial, so it's far away, so they would form the hydrogen bond. Okay, I'm stopping here, so we'll discuss the remaining topic in the next class.